Okay, so we are going to do today word search too. So in this particular question, we are given with, let us first read this question. There is, I've already written the code because it will take time to code this particular, that's why. So let us first read this particular question that is there, and then we'll check for the constraint and then intuition part. So here, given an m cross n board of characters and a list of string words, return all the words on the board. Each word must be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally and vertically neighboring. The same letter cell may not be used more than once. So basically in this question, as it is a variation of word search one only, but with the tightly bound constraints and even some more variation in the words which is being given to us. So here we are given with this matrix, this board which is being given to us, right? And the words which is being given to us, in which a lot of words are being there, and we are required to check about the are any of these words being present here. So that's what we are required to do here. Because in the previous question we were given with just one word. So that's why it was easy to do DFS in this particular matrix with that given word. But here we are given with a lot of words, and even you can check the constraints which is there. Although the matrix constraint is lower, but the total number of words which could be there is uh, 10 raised to power 4. So that simply means it's a lot of numbers which we are required to compare, right? So that will surely give us TLE. And although length of the word is 10, so that is pretty much low. But because of this only, if our solution is based upon the number of words, means totally dependent on this thing, then surely there would be a TLE. So in that context only, we are required to optimize the solution in such a manner so that we can go ahead with the non-TLE solution. So now let us first go ahead with the explanation for this particular question. Then I'll explain you that how to do. Let us observe some things in this question. That usual DFS which we do is something like that. We pick up that particular word from this particular word matrix which is given to us, right? And after that, what we are required to do is we are required to traverse in all four directions of that particular character, and according to the boundary condition elimination, and according to the fact that it is not matching, we are directly moving ahead in the same for checking for the right, you can say substring, which is not the substring but the right word which is being present in our matrix. So that's the thing which we are going to do in this particular. So doing that method means just doing the DFS. For the 10 raised to power 4 words, that would be really a huge number, right? In context of time. So in that context, let us foresee that there are various words which could be having the same prefixes. And with same prefix, if a particular word is not present in the matrix, then it could be easily skipped and word present could be pushed to the result. So as per the prefixes, we can sort all the words and such, not sort, but we can club those words with the common prefix and till whatever point it is having the common prefix. And after that, we can branch out the other words and just select that which word is the requirement of our input which is being given to us. So according to that only, we will be going ahead, and as per the constraint, doing only DFS plus the backtracking will give us TLE, right? So thus we need some data structure as per the above observation, means as per this particular prefix. So as per observation of prefix, preferred data structure would be a trie. So the thing would be, see that if apple is being given to us, right? So the trie would be having one starting node which is there, and corresponding to the same, there would be 26 further branches which are being there. And then corresponding to those 26 branches, we would be having a word which would be being stored in a particular branch. And in that also, we would be having some sub branches as well. Because of that only, we will be able to figure out that till this it is having a common prefix, and then there could be a word like apple is being present in our words, but this apps is not present in our word. So that way we will be eradicating this apps, but we will be able to figure out in just that particular DFS that apple word, right? So that's why with two different words with common prefix and reducing the time complexity. That's why this particular solution would be now completely dependent upon the length of the words rather than the number of words which is being given to us, because number of words here would be up to 26. That's for sure, because here 26 are the maximum try means maximum try nodes, not node try branches which are there. So that's why time complexity is reduced from that 10 to the power 4 to 26 in context of number of words, but now it is dependent upon length of the word. That's for sure. So now comes the part that how we are going to do this particular question. So first thing is that we will be creating a try for an input word, then do DFS in the grid given while comparing each character with strings stored in the try. So that's the thing which we will be doing in the same. Now comes the next part, that how we are required to code this particular question. So regarding the coding part, so for the coding part of this particular question, as we are going ahead with the try solution, so for that particular thing only, we first require to create a class for the try. So for creating the class for the try, as usual means, as per you can say means in most of the cases what we do is in the try node, because we are storing all the words and we are required with the common prefixes here, right? So we are also required to check that if that particular word is being ended or not. So in that context only, what we are going to do here is we are taking one member as string word and taking one member as vector whose data type is try node star and children is its name. And this is the constructor of this particular class. Here what we are doing is we are basically assigning 26 memory blocks to this particular children vector and initializing it with null. So that's the thing which we are doing here for this particular try node. And now comes the part that while using in our this particular function which is being given to us, the first thing is for using that try node, we require object. And by doing this, we are creating an object of try node class. And then first thing which we will be doing is why we use this try. Basically, we used this try to store all the input words which are being given to us, means all the input words here which are being given to us, we will be storing them in the try. Means rather than comparing directly with this vector of string which is being given to us, now we will be storing these words by clubbing them as per their common prefixes in our try and then doing the DFS for the same. So that's why we will be having this function build try where we will be passing this word so that all the words which are being present in this words that will be now add up in the try, and this is where our try would be stored. And here we will be storing an answer. And then here what we are doing is we are doing basically DFS. How we are doing this DFS is we will be passing the board which is being there because we are performing DFS on this particular board. And at each point for each character, we are comparing with the try node which is being given to us. So that's the thing which we will be doing. Now let us go ahead by for the insertion of our nodes in this try. So the first thing which we are doing here is we are first going ahead. See, here we are having this root and then we are allocating the memory in the runtime as per the try node data type. Now in this particular thing, what we are doing is that whatever word which is being given to us, means that vector of string, as per the length of that, we are first extracting the first word which is being given to us there, and then starting from the root point, then we are checking for that word which we have just recently stored, and then in that we are first taking the index of that word which is there. Now the thing is, I know I used that. So here, this particular words which is being given to us, right? Then this first word which is there, that we are storing here. Now this try node current equals to root. This simply refers to that the start which is being there. So now we are pointing at this point because this would be having a lot of branches, right, up to 26. Now we are pointing at this particular point, at this start. So this is what we are doing here. Now this particular words which is there, we are going up till its length, means basically traversing this vector of string which is being given to us, and we are taking this word here, and then what we are doing is that here we are basically checking in the start which is there. So let us first take this oath. So oath will be 15th because O is 15. So here we will be having null pointer because at the starting we have initialized it with null, right? So here it would be null, right? So as it is null, so what we are doing is we are allocating the memory at this particular point and then moving ahead to the next of this. Next year also it would be null only. So now this current has been moved to this point. So that's the thing. And here we have already filled our O which is being there. Now this block is already filled. So this we are going to do for all for a particular word. And then when that complete word is filled, then at the end means at the end of O, A, T, H means all these blocks. Then at the end block, we will be basically storing whatever word is being there. So this will be referring that now it is the end of this word. So that's what we are doing at this point. And then when all the things would have been done, this would be done for all the words, then we are directly returning our root. So that's the thing which we are required to do in this uh, build word function. Now comes the part for our DFS because here first thing is that we are building our trie which is being there. Then here we are doing the DFS on our board. So that's the thing which we are doing here. And after that, what we are doing is we are performing DFS on our matrix. Actually, this DFS is somehow that similar only the way we were doing in our word search one. But the thing which here changes that here we are taking multiple words as per the trie. So in context of that only, we have changed our base condition and recurrence relation is somehow same only. That recurrence relation is like we are traversing in the upward direction. We are traversing in this is left direction and this is right wait, no, so as per the here ij would be there. So here j plus 1, here I plus 1, here j minus 1 and here I minus 1. So this I minus 1 is basically the left direction. J minus 1 is the down direction. So these are the all directions which are there. What the things which we are doing here. So recurrence relation would be as it is that going in all four directions by keeping the check that the subtraction or addition which we are doing, so they are not making them out of the boundary. So that's what we are doing in this particular thing. So here, first what we are doing is that we are marking here as visited by doing this. And then here board of ij equals to see that we are doing at the backtracking step means when all these things would have been done. So at that point only we are doing this particular thing. Now here the first thing would be that whatever character is being there, so we will be storing at this point. And then if I see equals to hash means it is at the starting point only. Or if p children c minus a, c minus a simply represent that at that particular index this not simply represent equals to null means there is nothing there. The way at the starting when we were inserting earlier on nodes were null only, right? So that's why if it is at this particular point, then we will be returning. That simply means that that position we won't be getting anything. And then if this is not the criteria, means surely there is present. So then we will be moving ahead, means changing the position of our p. So here if I word dot size, that word dot size, see, at every point of this particular trie which is there, means at every point of this trie, we are having like here A, then B, then C, means basically indices which are there, right? So at each point we are having some word length. Here word length equal to 0. Here word length is also 0. Means until we reach the end of that word, means if apple was being stored here, right? So until we reach at this E point, means here only the word length would be 5, else at all of these points it will be 0 only. So that's why we are saying that if our word dot size at that particular point is greater than 0, then we are going to push that into our result, and at that point we will be making it as blank. So that simply refers that we have already traversed at this particular point and we don't require to go at that point again. So that's the thing which we are going to do in this particular portion, and this is how we are basically comparing with our try notes and our matrix corrector while doing the DFS. And now comes the part for the time complexity and space complexity. So the time complexity for the same is m into n, because we are doing DFS over the matrix of n cross n, into 3 raised to power L. Now why 3 raised to power L? L is basically the length of the longest string which is there. So M into N is basically length width of the matrix and L is the length of the word. That is when we traverse, then we could go in 3 direction only when we are inside a word each time. And how 3 direction? You can clearly see that if this word is there, right? So we can go in at any particular point in 3 directions. So that means basically we are having just those 3 choices, that we can either go in the downward direction or we can go ahead in other 2 direction for the same. So that's why just going in these 3 directions, and then comes the part for the space complexity. So space complexity is on the basis of that recursive stack which is there and on the basis of try. So basically try whatever the longest length would be there for our L, which is there, means basically longest length of a particular word, into 26. That is the 26, because at max we can store 26 words only, right? Means 20 starting words will be 26 only, right? Means from 0 till 26 would be there, but after that there could be more branches for a particular word, right? So that's why it is the space complexity is on the basis of 26 into L. And about the recursive stack, so in the recursive stack as well, whatever at max we can go is as per the L only. Means in the recursive stack also, we can go at max till the length of the longest word. So that's why it is plus L. So that's why we can directly go with L. The space complexity would be equal to L. So that's the thing which is here in this word search too. And anything else is not left. Yeah, this was all for this particular question. If you have any doubt, you could comment that down. And if you like this explanation, then please do like this video and subscribe to my channel and also share among your friends. So this was all for the same. Thank you.